Okay, welcome to the session practice session 2. In this, we will try to what do you call simulate the methanol water system distillation using a rating calculation. That means using the distillation module in the column available of the proton. Previously, what we have done is we have taken shortcut distillation, but in this case, we are going to take a distillation module which is used as a rating, simultaneously designing. It will help in designing of the distillation tower. With designing, I mean if we give the specifications, you will get the number of theoretical trays and you can decide upon which is the feed tray location. Okay. In the question number 1, we have solved using shortcut distillation operation, shortcut distillation module, and this is a shortcut distillation. And with this, the results which were obtained, I have kept it here in the screen. You can see if I take a total trace of 8, you can see the first row, R by R minimum, it is fixing as 1.75, and I have reflux ratio, accordingly it is 1.152. So these calculations are from Fensky equation, and there are correlations, empirical relations which it calculates actually. So let us consider this methanol water distillation here and the results obtained from this place. Number of theoretical trays is 8, R by R1 is 1.75, so reflux ratio is 1.152. We will see the feed tray also, it is given as 6.58. We can nominate this feed tray as 7 or rather 6 in our rating calculation. Now, when we say total trace is 8, in a rating calculation we have to specify 10 rather than 8 because condenser and reboiler also are calculated as trace. Okay. Now, let me save this file. Let me save this file as it is as Q2, that means question 2 rating, or rather I can say distillation module available in the proton. Okay, now I will actually remove these two this particular item here, and now you can see what is happening here, right? Now I'll remove this shortcut distillation tower in this place. I obtain, you can see in the columns, the general pressure change column. I'll go to this column and then obtain this distillation tower and then try to keep it here. Then it is asking me how many trays are required. So there is a condenser and reboiler by default is checked because we are going for a distillation operation, right? And then here, as we have known from the past question, or from the past solution, there are 8 trays. I specify here 10 trays, which means one condenser and reboiler also taken into consideration. So my setup, my distillation column is ready here. So I have to attach this feed to this place. Yes, so let me show you how to attach. This is the feed tray, and this is the top. You see, there are two red color nozzles here. I have to take the bottom red color nozzle because we are assuming it to be as a total condenser. If it is a partial condenser, then we'll go for the top red color nozzle. Now in the bottom also there is a once I click the stream here, I'll get to actually attach to the destination, to the source of the stream, right? So let me actually get this stream here. Yeah, I think this is going astray. 1 minute. Yes, so now I'll actually keep the stream. Okay, keep the entire thing at one place. Okay, cool. Now entire thing is operating at one particular position, so it is looking concise and beautiful while simulation, right? So now see, there are, I will have to go to input streams here. I said this is entering at subcooled liquid, so we have taken it as 20 degrees centigrade. That means if I want to see it in centigrade, what do I do? Convert the value. See, this is at 20 degrees centigrade and pressure is 1 atmosphere, but it is given as kilopascals, 101.325 kilopascals. I go to unit operations and then I say atmosphere and convert the value. You can see 1 atmosphere. Now flow rates, individual flow rates, methanol is 14,460 kgs per hour and water is 10,440 kgs per hour. So we are ready with this particular stream inputs. Then components are given. First you should take care of the units of measure. You have to change the units of measure to SI units as per the problem specifies, and go to the component section, specify the components here by typing it here or by selecting the components from the database which are available in the Port2, and then go to the thermodynamic model. Thermodynamic model, generally if there is a water, you look for NRTL first, and then select the NRTL from the most commonly used what you call property correlation system, and then take it into here, and we are ready. uh, Forget not to actually save when and where you are trying to actually operate, right? Now if you see in the whole process flow sheet window, this total what do you call, what we say this to be as a process flow sheet window. Okay, you should actually process flow sheet window. I'm trying to actually type it here so that you can actually appreciate better. This is a process flow sheet window for methanol water distillation column system, right? Distillation or simulation. We are trying to simulate, and simultaneously it helps in designing also. So what is the difference between design and the simulation? Simulation is that we, after running the with a given inputs, once we change any input, how the output varies, that facility will be available in the simulation operation. Now there is only one red colored mark what you see here, that means tower 1 T1. So I double click on it. You see there are many red colored, boxes available here. I go to pressure profile, and then I specify here pressure, that means 101.325 kilopascals, and then I feed, feed tray. We have given around 10. Let me say it as 6. Okay, feed tray, and we have to give either overhead or the under bottoms some initial gas, so that to start the numerical method to start the. So we have specifying in the what you call kgs per hour. Feed, in the feed we have methanol around 14,440 or something. So we wish to actually have maximum there. So let me type it here around 14,000 kgs per hour as the process operation there. Now still there is something called performance of specifications. Go to there and then come to this, and then see by default the two columns specifications are available. See, this is specifications. Column 1 spec 1 is actually 14,000, but we will not limit to this. We will actually change this here actually. And then column 1 spec 2 is what? Reflex ratio. But what is the reflex ratio? We intend to actually take it here in this particular, if you can see here, 1.152 from the previous results. So I change it to 1.152, and I wish to actually, in the column 1 spec 1, I wish to change it to composition of the more volatile component. More volatile component is methanol by default, because its boiling point is 65 degrees centigrade only, 64.5. So open this, and then I cannot specify 14,000 to be as a composition, right? So let me actually give it as a try, saying that it is 0.90%. Okay, I'm not actually giving it a 99% purity at once, but I am trying to give it as 90% first one. What are the outputs it will give us? What are the variables? You can see the bottom box, what you see here, these are the outputs we can actually specify. That means we will actually able to obtain the results and analyze. Column T1 duty of the heater condenser, column T1 duty of the heater reboiler. That means reboiler is present at the bottom, condenser is present at the top, so we can actually understand what is happening here, and then we can see the results. So I have changed the specifications in the two, that means reflex ratio as 1.152, and in the top stream S2 the methanol composition is 90%. That is what my wish, that is in the mole basis, please remember. And in this box also you can see the algorithm is inside out, number of stages is given as 10, number of iterations is 30. So when the number of iterations is 30, generally you make it as 200, so that the convergence, we don't have any problem with the convergence, or you can even build it more also. There is no issue, but if you increase the number of the iterations, it will take time to actually converge, and then the results will take some time. Now, so our inputs are ready. Now save it again, and then go to restore input data, restore write. So these are the data which are ready. Now we will try to run. See, now that means indication of the blue, it seems that our program or simulation run successfully. So what is the specifications we have given in the performance specification of the column? It is 0.90% and reflex ratio 1.152. Let me check here. So I go here, and then output stream here, right click here, and then molar units, and then open it up, you see this, there is a 90%. But it all results in moles, but we are interested to actually understand in mass also, because our units are in mass. So you can see total output which is coming as a distillate is 15,356 kgs per hour, whereas in that methanol is 14,453 kgs per hour, and it is by mass percentage it is giving us 94%, and we have asked mole percent as 90% mole, 90% in mole basis. We can also change that as mole fraction to mass fraction and then check if we can actually do it. But now I am not satisfied with 90%, 90 mole percent. I want it 99%. So I will actually double click on it, go to performance specification. I change it to 0.95. Okay, in the top section my methanol specification should be 95. Right. So let me actually see with the same reflux ratio I am trying to run. Yes, so it is actually giving 95% mole basis, and we are getting the results, required results. So if I see the mass basis here, what is my input here? What is the methanol? 14,417. Mass percentage is 97%. As it is in the feed, how much is there? So let us actually take that also and then check all the three. In the input, what is the mass? In the input we have 14,460 as our methanol, and in the output what is the methanol? So if I see this methanol here in the output also, you can say 14,417 kgs, and whereas in the input what is the mass here? 14,460 is there. So 95% we have asked, but this is mass percent it is showing, but it is also running. But if I change it to 0.97, will it work? See, now again go to this place and then restore input data, then save it if possible, and then run the program. Now see, it is not in a position to run. So there is a certain limit with the given conditions and the reflux ratio, with the given input flow rates and the conditions. This is what it is trying to actually give us. That means up to 95 mole percent we are able to get the output, but beyond that, okay, I have not tried 96%, but I have tried 97%, but it is not going. So what is the best option? What we can do is that improve or increase the reflux ratio. So this 1.152 and I randomly increase to 2 and try to actually solve the same problem. That means with the 97% of the requirement, one of the specifications is 97%. See, this is 97%. So when I restore input data and then I run it, now you see it is running. So let us check the results here. See, the 97% mole percent is coming as our output, but still more greedy, or still more, let us actually assume I can get 0.99. So let's see again. Well, let's see again while running this program and but still it is not in a position to run this program. Okay, now I go to performance specification. I enhance this 2 to 2.5. That means the reflux ratio is increased from 2 to 2.5, and then again I am running it, run the program, still it is not able to run. So I think there is some cut point, there is some limitation in this, because we have to get it theoretically cleared and then you have to come out, or you need to put a logic here. You have to play with the number of trays and the reflex ratio. I think more than 3 or more than 5, it consumes a lot of energy. You have to think and then do it. But with the 1.15 to whatever we are seeing in this particular text here, we are only able to achieve up to 95%, 95%, 95.5% only. Beyond that, with that reflex ratio, it is not possible. Okay, so we will go back and let me see if it is 98% runs here, 0.98, and 2.5 is the reflex ratio, and then I run it here. Yeah, but still this also is not a problem. This also is a problem. I go to retain it as 0.97, 97 mole percent. It is saying 97 mole percent here, and run it here. Now see, up to 97% it is fine, but beyond 97% there is an issue. Okay, with this I complete this video. I'll come back with another exercise wherein we don't have to actually every time change one input variable or one specification and the how the output varies. There is one more analysis called sensitivity analysis, wherein we use a case study, what you call tab, available in this program. Okay, take care, and then we'll meet in the next exercise session. Hope you have understood it. Do share across your friends, and then if you have any doubts, you can actually write to me, and I'm ready to help you.